about Fairmount. So as Dean mentioned, and thank you for your kind remarks, we're investment bankers to growth stage companies. We do sell side M&A, we do later stage capital raising, but we are most at home working with companies that are using new technology and finding new ways to implement it, and are doing really cool things. So that's what we do at Fairmount Partners. And I am very pleased to introduce the next part of our programming. So let me kick that off. So first introduction, a pioneer in computational thinking, and in 1981 the youngest ever recipient at the time of a MacArthur Genius Grant, Stephen Wolfram has been enlarging the scope of knowledge-based computation since he began developing his Mathematica system for technical computing in 1986. He is the creator of Mathematica, Wolfram Alpha, and the Wolfram language, the author of A New Kind of Science, the originator of the Wolfram Physics Project, and the founder and CEO of Wolfram Research. Over the course of more than 4 decades, he has been a pioneer in the development and application of computational thinking and has been responsible for many discoveries, inventions, and innovations in science, technology, and business. Peter Coffey, VP for Strategic Research at Salesforce, has been with the company for over 15 years, and when I think about it, most of those 15 years he has been a contributor to this Forum conference, and we are very, very thankful for that and for his guidance and for his participation. His global work supports C-suite teams, data governance professionals, and innovators in connected products and big data domains in many industries and institutions. He also advises on curriculum and degree program planning and analytics and big data initiatives for 3 U.S. universities. He is co-founder and president of the Foundation for Intelligent Life on Earth, a Seattle-based sponsor of efforts addressing climate change, conservatism, STEAM education, and exploration of Earth and space. Please welcome Peter and Stephen for what is sure to be a very illuminating conversation on generative AI.
Thank you so much. I'm going to do one quick edit on my intro. Conservation, not conservatism, or is one of the goals of our foundation, and there is a slight but rather important nuance there. Stephen, it is such a remarkable coincidence to have us both in this same space. It's like having 2 long period comets both orbiting the sun at the same time. We haven't had a direct conversation in so long, but it feels like, yesterday. The phrase that comes up always when people are describing you in the manner you prefer to be described is computational thinking. And at a time when so many students are off to college and picking majors, or about to graduate and picking careers, and they're asking me, and their parents are asking me, well, should they be a computer science major? Or people are asking me in the inner cities, should we be sending the kids to coding clinics? I don't think computational thinking is computer literacy or computer science. I certainly don't think it's programming. What is computational thinking? Why does it matter? How should people recognize it and develop it and apply it in every domain?
Right. So, I mean, the thing about computational thinking is computation is this paradigm, this way of thinking about the world, this kind of organized, formalized way of thinking about the world that also happens to be something where we can get a lot of help with it from computers. But the question is, if you're trying to address some question, I don't know, I'm looking at your background there, maybe you have some plants in the background, I don't know. And let's say we want to think computationally about those plants. We might say, what's the, we look at the image of you, we say, what's the area covered by leaves in that image? What can we say about, how do we think about, the shape of these leaves? How do we imagine how that works? How do we think about using machine learning to identify what kind of plant it is? Those kinds of things. The question is, how do you take kind of the things that we deal with kind of every day in the world and formalize them to the point where we can get a computer to help us analyze what's going on? It's really, the way I think about it is, back in ancient history, things like logic got invented. Logic was sort of a way to take what would otherwise be somebody just making some rhetorical argument and say, let's see how we can formalize this rhetorical argument to find out whether the pieces actually make sense. That was kind of the role of logic. Now we get to do that across sort of every domain of human endeavor. We get to say, how can we kind of formalize what's going on and talk about it in these kind of precise terms that then we can have a computer help us to deal with. And if you think about these different fields people do in college or whatever else, there's for every field X, there either is now a computational X or there will be. And that computational X is clearly the future of that field. Now, a question is, how do you get to the point where you as a student, for example, can do computational X? Well, really the most important thing is, how do you think about the world computationally? The question of how you write kind of, what's happening at the low levels, writing code and so on. People like me, I've spent the last 40 years trying to automate away everything I can of that process of going from the way you think about something computationally to its actual implementation, on a machine. And that's, and I think, what we've seen recently with the whole ChatGPT generative AI story is something which I have to say, as you know, I've been kind of pushing for decades now, this idea that there's a lot that can be automated in the programming process, so to speak. And that's something that, is all the more evident now. Now, in the end, you say, well, I can just, tell ChatGPT what program I want to write, and it's going to write it for me, just like I can tell it what English essay or, what letter I want to write, it's going to write it for me. At some point in the end, you have to specify what you want. So there has to be, and when it comes to programs, what one's typically interested in is not just having this one short little piece of code that does one thing. You're interested in building some whole tower of functionality. And if you do that, it's important that sort of every brick that's put down in that tower be nice and solid. You can't be, it's like, oh, well, that first brick wasn't quite right. It'll be okay. It'll sort itself out later. No, it won't. The tower will fall over later. So, we're in the situation where it's we still have to have a way to kind of specify precisely what we want. And that's what computational thinking is about. That's what kind of the idea of computational language that I've so long been involved with is about. Is how do you get a precise specification of what you want? I mean, it's kind of like in English, we're used to, we say things, we say them somewhat vaguely. If we're writing a contract, we might want to write it in legalese that tries to, take English and make it more precise, so to speak. Computational language is kind of the limit of that. It's making everything sort of as precise as logic, so to speak, in describing what we want and how we want to set things up.
It's so interesting to imagine that we're at a sort of cusp here where people who grew up without access to the power of connection and computation, when they design a process, perhaps quite unconsciously, they do it from a perspective that computation is expensive, that mathematical skills are rare, and they design a process that can be done without computation, and then they ask the computer people to come in and automate that process, as opposed to having designed a process that would make more effective use of computational resources because it was designed in a context of knowing that that's an abundant resource and not a scarce and rare thing. Where do we begin to get people thinking that way? Seymour Papert suggested we should be getting early elementary school age children to think about computation as an abundant resource.
Yeah, I mean, I think, what I've observed, so, I've spent a long time, building a computational language that tries to sort of express everything in the world in computational terms in a way that fits in well with the way people think about things. So, I don't know, you might start with a question like, how far is it from Philadelphia to London or something? And that can be stated in natural language like that. But then what you think about at sort of a computational language level is, what is that? That's the geodistance from the entity that represents Philadelphia to the entity that represents, hopefully, the correct London that you were thinking about, so to speak.
Yes.
It's kind of like, how do you think about taking a question like that, which, has a certain amount of, okay, what do you mean by geodistance? Do you mean the shortest path across the Earth? Do you mean, not in that case, but in another case, do you mean the driving distance? What do you mean? How do you think about making what you're asking precise? And I think this question of kind of how do people think about that. I think one convenient way to sort of imagine, if you have a business and you're thinking about, different kinds of things you're doing, and it's kind of like, how do you make a computational representation of the things you're trying to do in your business? How do you turn, when we think about, how do we turn something into this sort of function that is not just a job function of somebody, but a thing where there is some computational structure that represents the thing we're trying to do and some computational operation that we do on it? What would that operation be? And when you first start thinking about it and you're not used to kind of thinking computationally, it's all kind of vague. But when you get used to thinking computationally, it's something you can really you really design things in these terms. And I think you're absolutely right that one of the transitional moments is when you kind of start with computation in mind, so to speak, rather than starting with something where you say, well, we're going to tighten it up later. I've noticed a few things I've done in my life that well, for example, when our Mathematica product first came out in 1988, one of the things, its sort of first big market was technical computation folk, physicists, mathematicians, things like that. Those people had never been able to compute with their own fingers before, so to speak. They'd never been able to actually type something where they could compute. It was always let's take the thing we're thinking about, let's ask a programmer to code it up. Then 3 weeks go by, the programmer comes back, the person's forgotten what they asked, the programmer's come up with something different. It didn't really work very well. What Mathematica enabled, starting in 1988, was this very tight loop of the person who's thinking about the question gets to sort of crispen it up by saying, well, how would I say that to Mathematica, so to speak?
Yes.
That kind of is a way, it's kind of like, it's the way of kind of sharpening up what you're thinking about. And then you're in this kind of tight loop where you get an answer back and, well, it wasn't quite what I expected. And, let me keep going and now understand something. And, in a business context, it might be, can you, the executive, kind of yourself ask the question about, some aspect of what's going on in the company. You get the result back and it's, well, that's not what I expected. Let me, maybe that's because I asked slightly the wrong question. Maybe that's something else. Can you make that a tight loop where you're able to sort of get answers that you can immediately do something with, rather than this kind of very slow process? And that's enabled by people, from executives to kids, being able to actually think computationally about things themselves. Now, in terms of the sort of education process, the main sort of type of education that has tried to get people to sort of think crisply is mathematical education, which has not been, I would say, a complete success. Because for many people, the main thing that they take away from, math education is, I don't like math, I'm not very good at math, things like this. And there's a small fraction who go on and become, distinguished mathematicians and so on. But it's and part of what happened there is that the kind of the thing that was, when sort of math education was set up as it is today, like 100 and something years ago, sort of calculation was the focus of what was going on. One didn't have calculators, one didn't have any of these kinds of things. It was all about how do you mechanically calculate? And that's the focus of what people were doing. Now, of course, the calculation part is completely zeroed out. And even, math education is not really adapted to that. In terms of computation, the part that involves kind of the low-level programming type side of things, that's in the process of getting zeroed out. I mean, I suspect you, like me, probably, the first computer language I learned was assembly language. Don't know what it was for you, but that was, back in the day when I started dealing with computers, people would say, if you're going to write a serious program, you should be writing it in the assembly language, like machine code, like stuff for the computer.
Yeah.
And, then a few decades go by, and it's like now, nobody's writing directly in assembly language. Nobody
Hardly now. Yeah.
I mean, it's a tiny fraction of people. And because there's sort of a layer of automation that is much more suitable for the way people think about things, rather than this kind of way of worrying about, the micro details of the computer.
And I think you're making a key distinction here. Computational thinking does not mean learning to go to the machine and talk to the machine the way the machine wants you to talk to it, but means imagining what the machine could do but relying on layers of abstraction to take your question, and also not to obsess over, I have to ask the question in exactly the right way, because otherwise the machine will give me a correct answer to the wrong question and I'll be screwed.
Yeah.
But the idea that there will be an iterative process in which my first attempt at the question will produce an answer that I'll say, oh, okay, I see what you didn't understand there, and there will be an expectation. There won't be a bug, it'll be a feature that we are now asking iterative questions instead of that being perceived, oh, you did it wrong. No, I didn't do it wrong. I asked an initial question, it got me an initial answer, and I'm going to converge on how to ask the question I really want answered.
Right. No, I mean, I think that, the key thing is sort of how do you formalize how you think about the world? And that's something which, all of us kind of, in sort of everyday life, you kind of do things sort of by off the top of your head, so to speak.
Yes.
But then there's the question, when you want to build a solid structure, how do you do it in a way so that that can really work? And, we're seeing, with the whole ChatGPT story and so on, it also is good at doing kind of off the top of your head type things.
Yes.
It's not good. It's not set up to do, and it's not good at doing kind of the deeper, let's actually build a solid computation and build many layers of capability and so on. And so,
Stephen, is there any branch of academia that is teaching computational thinking as opposed to teaching arithmetic or mathematics or calculus or analytics or linear programming, or, is there anyone who's teaching how to approach a problem from a point of view of computation's abundant and I'm going to structure this problem in a way that uses that resource?
There are, there's sort of a dotted around the world.
Okay.
For decades, there have been people doing really, really great stuff in these areas. Okay. I would say that what I'm kind of expecting, and it looks like it may fall to me to actually define some of how this works, is, people talk about CS. Everybody wants to do CS because everybody knows that computers are important in lots of different areas. And so they say, well, that means we should study computer science. That's not really right, because a lot of what computer science has turned into is learning to write programs in programming languages that kind of, as you were mentioning, kind of pander to the details of how computers work. The thing that I think is, is the real story is kind of learn to define things computationally, then expect people like me to have built layers of automation that let you go from the thing you define computationally to actually, working out the image processing of the scene or whatever else it is. And I kind of think, it's kind of what we're going to is for all fields, we're going to sort of the computational X. And so I guess my best summary so far, and maybe I'll come up with a better one, is, you don't want to do CS, you want to do CX. CX kind of this understanding the principles of computation. And it has not been as well codified or formulated. Like, what's the curriculum for CX? Yeah. Well, lots of people have said to me, you should make that curriculum, and probably I'll end up doing that. But that's it's something where it's it's an emergent thing, and I think we just got a big kick a few months ago with the arrival of kind of ChatGPT and so on, to say, yes, this idea of CS education where lots of people are kind of learning to write low-level programs, it just doesn't make any sense. And
now, you've also used often the phrase knowledge-based computing. And one of the remarkable things about being exposed to the Wolfram language is you suddenly say, wow, why don't all languages include the ability to pull in data about the real world as a programming language operation instead of treating it as some separate world of database queries or whatever? It's remarkable to have things in the Wolfram language that are operators on knowledge of the world, with the assumption that, of course, that's available. That I think is maybe one of the most fundamental distinctions between your approach to how programs should be designed, not a world of cogitation separate from a world of knowledge, but the knowledge and the operations on the knowledge being much more integral with each other.
Right. I mean, so, the history of programming languages is first, the computer was really expensive, and, the human was going to do a lot of work to figure out, what was that one or two operations the computer was going to do. The strange thing about programming languages is they, the details have evolved a lot. The principles have not evolved that much. It's still very much, a computer stores things in memory here. It has loops, you can make arrays. it's very much pandering to the way a computer is set up.
Yeah.
My interest has been, let's take the power that comes from being able to do things computationally, but try and connect it to the way we think about things. And one critical aspect of that is there's the real world out there that has, all kinds of data, knowledge, all kinds of models and methods and algorithms and so on. Let's just automate having direct access to it. I mean, kind of the way I think about it is, if you look at the evolution of computers, back in the day, computers were just raw computers. Then they got, then you came, operating systems became sort of a standard thing. Then later on, networking became a standard thing. Graphical user interfaces became a standard thing. My long-time goal, and it's now in the process of really happening, is to build a system where you can expect to walk up to a computer and have it know things about the world, have it know, what are the coordinates of every city in the world? What are the history of the populations of every city in the world? What's the, the method for computing something in chemistry? What's the, all these kinds of things that are part of the corpus of knowledge, both data and procedures, so to speak, that we've accumulated as a civilization, and bottle that all up in what you can expect for a computer. Now, the internet has provided kind of textual access to a lot of knowledge. What we've been interested in doing is kind of crispening things up to the point where you have kind of sort of solid, systematic, computational access to that kind of knowledge. So, on the internet, you might be able to find, one site that says, the density of this material is this, and another site might say something different. And, they might have some convention for figuring that out, but, you don't really know what it is. But now you want to compare 5 different materials and you get them from 5 different websites, and it's all kind of messy. Our goal, and the thing we've spent the last few decades doing, is trying to curate data about the world to the point where it is solid enough that you can systematically compute with it. And it's a lot of work. It's been kind of, I think it's been this kind of unique thing that we've done. Now that becomes very important in many cases. For example, in both figuring out things about the world as it's sort of publicly known to be, and also when you're dealing with your own company, organization, whatever else, being able to mix kind of the data of your company. Oh, are we selling what we would expect to sell in country X based on some metric that's based on, number of internet users in that country, or population of that country, or GDP of that country? Being able to have that kind of systematic data that you can mix in with things which are sort of your own sort of personal or organizational data, that's turned out to be really valuable. But this idea that the programming languages I see as being kind of pandering to, this is how computers work underneath. This is how we we as humans kind of serve the computers, so to speak.
Yes.
The concept of our computational language is, this is how we think about things. Thinking about things computationally gives us this way to crispen up the way we're thinking about things. Kind of, we're in charge, and it's a question of kind of getting computers to do the things that we want to do, so to speak.
I've compared what you're talking about to learning to drive with a little trap door in the floor, and when you want to shift gears, you reach down and rearrange the gears. Building a robot to do that for you will not lead you to the automatic transmission. At some point, you need to adopt a new thought model for what is the thing being done, and not just build a robot that does that thing for you. But you've mentioned a really important point, which is that I go look up the density of a material, and I might find different values in different places. Jerry Pournelle at Byte, if you can remember, used to talk about someday we'll live in a world where anything that can be calculated, or anything that anyone knows, you'll be able to find out. We're arguably there, but perhaps we've overshot it, and now we're anything that anyone believes you can be told as if it were truth. And now I think we're getting into something that you have written about, which is, please don't confuse what a generative AI does with telling you the truth. It doesn't have a concept of truth. It's just trying to make a prediction. And I feel like people are going to feel like they had a bait and switch if we don't spend a lot of time talking about that kind of tension.
Yeah, well, I mean, the thing to understand about, the ChatGPTs, the large language models, LLMs, and so on, is, what are they actually doing? What they're actually doing is, they're trying to write text that follows the prompt you gave and is sort of statistically like the trillion words that they just read on the web, right?
Yeah.
So, the ultimate operation of ChatGPT is you have written a certain collection of words. You might have written 50 words that says, I'm interested in this and this and this. And then its underlying operation is figure out what's the next word going to be. And one way to, let's say we had a sentence like, the cat sat on the. Okay, what's going to be the next word?
Mm-hmm.
Well, we look on the web, and I'm sure there are 50,000 places where the next word is mat. There are, 3 places where the next word is fishbowl or something. And the sort of the most basic operation of an LLM is to say, let's look at the statistics of what's out there on the web, and let's try and continue this sentence to follow kind of the typical of what's out there on the web. Now, the fact is, as soon as you get to any prompt of any significant size, there just isn't enough data on the web to be able to say, oh, let's look at what's already there that's just like this prompt, because you probably just wrote a prompt that nobody ever specifically wrote before.
Yes. Yeah.
So that requires having a model to make the prediction. It requires that you can go beyond just saying what's statistically out there. And that model, the big surprise, which I think we learn a whole bunch scientifically from, is that neural networks turn out to be a model that correctly gives us words, allows us to make those kinds of predictions in a way that agrees with the way we humans seem to do it. And this is probably not surprising, because the fact is the way our brains are architected is very similar to the way a neural net is architected. And what we're really seeing there is that this simple idealization of how brains work does what brains do, and is able to give one kind of the next word, next word, next word. But again, what it's always, in a sense, trying to do is it's trying to make you a piece of text that is kind of typical of what you would find on the web. And so the question of whether that's and by the way, when you say typical, it's kind of like it'll do things like it'll say, oh, I don't know, you'd ask it something about, the density of something, and it would say, well, according to this source, the density is blah. It didn't look up that source at all. It knows nothing about that source. It's just noticed that on the web, most people who talk about densities of things quote that source. So it trots it out and says, according to this source, blah, blah, blah. And, so that's what it's doing. And by the way, I mean, just to understand there's great utility in that. And I think one of the things that nobody saw coming is the way in which something like ChatGPT operates as what one can call a kind of large-scale linguistic interface. We've had graphical user interfaces, but what's happening here is, let's say you've got, 4 points you want to make in some report you're writing. Well, you can jot down those 4 points. But if you actually just handed your raw 4 points to somebody, they probably say, what are you talking about? I don't understand this.
Right.
You feed it to, a large language model, and it's going to puff that out into a whole giant, report that's written according to the standards that people expect the report to be written according to.
Yeah.
And then people can read it and say, okay, great. Now I understand what this person is talking about. That's all good. Now, I mean, the sort of in a sense, irony, but the reality is, in many cases, that report will be read by another large language model. It won't be read by a human.
Yeah.
And, but then the process, which I think is sort of interesting to understand, is, you go from the initial points the human was trying to make to this kind of interface of English as this report. Then the other LLM at the other end condenses that down to the 2 points that the people who were reading that report really cared about. And then you can kind of go on from there. Now, that's a process, this sort of, that's kind of the way that this operates. Now, that's to be distinguished from kind of what happens in sort of the computational language world, where you have a very precise definition of what you want. You are sort of computing something, and then that's the result. Now, and for example, one thing about sort of computational language and doing computation is you can compute things that have never been computed before, that have been, that are fundamentally new knowledge, so to speak. When you're dealing with a large language model, what it's doing is essentially regurgitating kind of some average, in some sense, of what we humans have put out there on the web and in books and places like that. And I mean, this question of sort of what's what's true. Well, at a linguistic kind of, is that a reasonable sounding thing to say? A large language model would do great at that. Is it the precise thing that would allow you to, shoot the rocket to the moon and not miss? It's going to do horribly at that. It's not. That's not what it does. It does kind of, does it sound right type? It answers. It does well the kind of doing things where the result sounds right, so to speak.
It's interesting to imagine that the easy thing to do impressively well at low cost was to just turn it loose in the public feeding trough of the internet and demonstrate what it can do with an enormous data set. As Irene Rombell was saying in a session earlier today, most of the world's real value probably lies in what she termed, technically phrased as the small crappy data set. And the question of how can we apply the natural conversational iterative interactive mode with data to data sets that don't have the sheer enormity and mass of the public internet. And then also, I think I'm hearing you say, it's going to be fascinating when you don't just use the generative AI to produce something, but also use it in a more personal way to help me understand, digest, and summarize this. And to your point, if someone's got 12 bullet points and generative AI can help flesh those out, but then you can say, someone's just written this large thing. Tell me what he had to say about these two things. That's like an impedance matching network in electrical engineering sense. What a remarkable idea to turn language into something we can manipulate that way.
Right. No, it's a very useful thing that I think none of us saw coming. I mean, because I think what happened, I'd been following, as many other people have, I've been following neural nets since 1980, actually, when, I first started simulating them then, and they didn't do anything at all interesting. And even last year, the language models that existed weren't quite to the point where they were really very interesting. They were just kind of, they could fix some grammar and things like this, but they weren't like, I can actually write a compelling essay, so to speak. And I think it's nobody could predict, when one would reach this threshold. I think sort of a historical analog that's perhaps interesting is what happened with electricity and telephones. So, people had invented electricity. It was known from the, early 1800s and so on. And, just like we've known about computation now for a long time, but this question, and people realized that, yes, in principle, you could connect, a microphone to a speaker and you could transmit human voice over an electrical connection. But it didn't work. And at some moment, Alexander Graham Bell did his kind of surprise experiment, and he, had managed to do the engineering to the point where suddenly it got above this threshold where people can say, yes, I can understand what's being said at the other end of the phone. And I think this is the same kind of phenomenon, that we just sort of reached this point where, the text that got written starts to seem compelling.
And it is an important transition. I'm going to squeeze in one last question before we go to the room, but I want to have the folks in the room ready to start bringing in the live Q&A. But Stephen, I want to ask you, if you walk into a room where people are talking about their desire to put generative AI to work, are there certain things you'd want to hear that would be green flags that say, okay, you're doing this in a way that's not terrible? Or are there certain things that if you do hear them, they would be yellow or red flags where you would want to say, danger, Will Robinson, what you're talking about doing is not going to give you what you want, either for good or ill? Give me whichever one comes more readily to mind. Well,
so I mean, one point, and it's true about machine learning in general, machine learning is great for the 90% stuff. If you want to get, if you've got something, let's say you're getting search results on, you're searching something and you say, I'm going to get 10 results. And if 2 of them are really exactly what you want, everybody's happy, you're a winner. But for a situation where all 10 have to be right, that's not something you should look to machine learning to do. And there are a zillion use cases that are, we're noticing every day. We're realizing new use cases for generative AI. I mean, to give you an example of a recent one, when you have bug reports for a large computer system, you can have the AI read the bug report written in English and go figure out where the bug, at least somewhat localize where the bug is. Not something I had imagined would be possible.
Very interesting.
But that's something where if it gets it wrong 10%, 20% of the time, it's like, okay, well, it didn't get that one. But when it gets it right, it's a winner, so to speak. So
that's a really great insight. Thank you so much. And now, speaking of a zillion use cases, let's go live to the room and find out what's on the minds of the perhaps not quite a zillion people who are with us in Pennsylvania today. Mike Bachman, our conference chair, I believe, is herding the cats. Mike?
Yes. Hello, Stephen. We're
Hello.
all here. Thank you. Do we have any questions? Irene. Okay, great.
Hi, fantastic session. Thank you so much, Dr. Wolfram. So I am probably one of the few people in the room that is not a programmer. I'm a chemist and molecular biologist by training, but I think one of the things that is common throughout is thinking about uncertainties and probabilities, and of course, it all boils down to what's the quantification of the uncertainty. And here, my impression is that with a lot of these tools, especially if they're in the public domain, nobody thinks about uncertainties. This is what you get. So how does, so obviously it's not incumbent on the end user because they will just blithely use what they're given. So how can we impart some kind of, I don't know if you can have regulations, but at least standards in terms of, so that the data has got some degree of accuracy, or at least people can quantify it and know, well, this is 50%, chance of getting it right.
Right. It's quite difficult. I mean, so in the notion of probability is, I mean, depends on your field. If you're doing clinical trials, for example, we just kind of imagine that biology is complicated, different things are going to happen, people are different, and there's kind of, there's this kind of, and something's going to work some fraction of the time. We can't really say, and then we care about that percentage, so to speak. Now, in the case of something like, a neural net, neural nets they are often, if you look at the insides of ChatGPT, what it's doing is it's saying the next word is this with that probability, is this with this probability. In fact, at every step, it's taking the 50,000 words in English and it's assigning a probability to each one of those words and saying the next word might be this one with this probability. And one of the big things that's kind of a weird feature of large language models is this thing that's usually called the temperature parameter, which is you don't always want to pick the most probable word according to its notion of probability. If you do that, you get a very flat essay, and sometimes it even just repeats itself. If you pick if you go too far down in the ranking of probabilities, the thing starts sounding really crazy. But this notion of probability that it's generating is, that notion of probability, how is that derived? Well, the way it's trained is you give it a bunch of text and you mask out the next word and you say, guess what the next word is. And then when you unmask it, you can say, well, that's what the next word actually was. And that's kind of its notion of probability is what was its chance of getting right the next word. So, when you think about kind of the foundations of probability, this is now I'm diving into basic science, but this question of what is probability? Is probability how frequently things occur? Well, you have to have a collection of things occurring to even define frequency.
Yep.
Or what's the kind of source of this notion of probability? But if you're asking the question, kind of, how do we validate something how do we say we know for sure that the AI did the right thing? That's not a good thing to get from AI. That's a thing you get from computation. From computation, you can say this follows from this, follows from this. It's kind of like logic. From the AI, you get, well, this sounded good, but you're not going to be able to get that sort of precise thing. Now, a place where this becomes very important, which perhaps you were alluding to, is kind of AI safety, kind of AI ethics, these kinds of things. When the AI is making a decision, and it's making a decision that has some significance in the world, how do we make sure it's, quotes, making the right decision? Well, here's one of the paradoxes of all of things that happen with computation. Let's say that we had perfect guardrails. We say, we know it's never going to do the wrong thing. We know we know exactly what it's going to do. Well, as soon as you say about a computation, we know exactly what it's going to do, why are you doing the computation in the first place? In other words, there's this kind of computational process that you want to go through, and there's a notion in basic science that I came up with years ago of computational irreducibility. The idea that you can't know what's going to happen in a computation more efficiently than by basically just doing that computation. So, as soon as you say, well, I'm going to know what the end result is going to be. It's like, well, why are you doing the computation in the first place? So we have this trade-off, and it's an important one for society to come to terms with. We have this choice. We either let computation and AI do things that are most of the time very valuable for us, but where we can't just say we know exactly what it's going to do, or we say, let's make it a simpler kind of machine where we can really see how all the cogs and levers are working, and we know exactly what it's going to do, but then it can't really sort of have achieve the potential that it has as a computational kind of system. So the trade-off between these things of how do you put up sort of constraints that say, well, we'll let it do this, but not that, and so on. That's a complicated and tricky area. I happens to be one that I've thought a fair amount about, although I don't consider that I have great answers for it.
Stephen, I believe I understand you to be saying this is not an immaturity of the technology issue that will work out in time. It is necessary to understand there are two irreconcilable goals, and you can pick your point on a spectrum between them, but don't expect the ends of the spectrum ever to converge into some grand synthesis. They are two different reasons for doing it, and you better know which reason you have in mind when you're constructing your system and your application built in that system.
Right, and I mean, as I was saying before, in the kind of if when it gets it right, let's say 90% of the time, you're a winner, and when it gets it wrong, it's not a big deal. That's a good case.
That's a good application. That's a great way to recognize an appropriate problem. That we don't have any good way of getting good answers now, and if we can get some good answers, any good answers, I forget what the exact ratio is, but you have to throw out an awful lot of dirt to get an ounce of gold. And if getting the gold, with hand shovels is not practical, but now we got power shovels, that's important.
To give an example in the generative AI area for biochemistry, which you mentioned, I mean, the whole sort of protein folding problem, which is a long time computationally difficult problem, a lot of progress made by basically matching up, being able to sort of see, well, what are all of how the protein I've just been presented with, how does the pieces of it correspond to all the other proteins whose structure is known, and then kind of gluing those together using machine learning to say kind of what's the typical way a protein works, getting that prediction. Okay, so usually it'll be roughly right. Sometimes it's not so right. But let's say you want to describe, I want a protein that will make a cage that will keep, I don't know, manganese atoms or something, in this little cage. It'll be the right size to keep manganese atoms. And then, you can have something where sort of generatively, you can start thinking about producing, here are candidate proteins that do that.
Yeah.
If you get just one winner out of, then you got what you wanted. And it doesn't matter that a lot of these things are misshapen, weird things where the AI kind of confused what was going on and so on.
Right. That's a great filter to recognize relevance and applicability. Mike, I hope we can get in at least one more question before 4 o'clock.
I think we do have one more question in the back.
Hi, thank you so much for your time today. This is amazing. It seems to me that the trend for the next acceleration of these large language models is kind of in the vector space, and a lot of the kind of endless loops and recursions that are occurring to accelerate this technology. But my instincts say that more acceleration would come from the non-Euclidean kind of graph theory or graph neural net space. I'd love to hear your perspective on whether you think the future is kind of vector driven or more non-Euclidean graph theory driven.
Okay, so the basic point about neural nets is when you don't know how a system works, it's great to use a neural net. As soon as, what I think we have learned from the success of ChatGPT is there are regularities in language that we just didn't know were there. Like, we know that there is a syntactic grammar of language. We know that nouns and verbs go together in sentences in a certain way. What ChatGPT is showing us is that there's a more extensive construction kit for language. There's ways of saying what goes with what to make sentences that make sense. The neural net found an incredibly, complicated way of doing that. I think one of the things that will be dramatic, and I don't know how long it will take to really happen, is to be able to say, and you can couch this in neural net terms in terms of encoders, decoders, things like this. But basically, the thing you're operating on is not just the pure words. it's some kind of underlying semantic grammar of language. And that will be, that will be dramatically more powerful. I think we can expect, I mean, when it comes to specifics of things like graph neural nets, yeah, I mean, there's a company that's actually following up on a bunch of science that I did about graph rewriting that thinks they're going to make a fantastically more efficient neural net. We'll see how that works out. I think it's hard to predict what, the way that current neural nets work, as I say, probably in the end, they're capturing a decent part of the essence of how brains work, which is why the neural nets can do the kinds of things brains do. Now, if you tell that neural net, do a thing that brains were not used to doing, like you say to that neural net, run this piece of computer code. Nobody runs code in their head, basically. Just not one of these things. People can do mental arithmetic, but they can't do code running in their head. It's the things that we humans do easily. These neural nets can often, are often able to do. The things that we humans can't do easily, that are kind of off limits for these neural nets. And I think, okay, my guess is that in terms of the dynamics of how things will develop, first point is the kind of neural net that's inside ChatGPT is actually quite simple. It's people in the, neural nets in the form that they are right now were pretty much invented in 1943, very long time ago, before there were electronic computers. And people came up with these much more elaborate schemes for having neural nets with all kinds of extra sort of apparatus in them. And it turned out that didn't really matter much. Now, why is that? I think it captures the essence of what brains are doing. And also, there's an important point about computers in general, which is this whole idea of universal computation. You can have one computer with one microprocessor, another computer, different microprocessor, but they can run the same programs. And one of the things I've discovered scientifically is that there are incredibly simple kinds of systems which are capable of being universal computers. And that means that, across a very wide range of different kinds of systems, they ultimately can run the same programs. So you say, well, I've got this neural net with this extra piece of apparatus in it. I've got this graph neural net as opposed to array-based neural nets, tensor-based neural nets. It's probably going to be able to run the same programs. It's going to, now the question of the details of efficiency will depend a lot on what kinds of problems you're giving it and whether the kinds of things that we're giving it, which are the kinds of things we humans do well, then I think it's going to be this question of sort of the alignment with the hardware that we have. Now, another point to make as a practical matter is what tends to happen in the computer industry is, people will come up with some way of doing things. And then people will say, let's optimize that way of doing things. Let's build special purpose hardware. Let's make these incredibly optimized algorithms and so on for that particular way of doing things. And it will turn out that even though there might be a better way of doing things, that will never actually be more efficient because, the special purpose hardware that's been made is, 100 times more efficient because it's been carefully optimized. And even though the better way of doing things will be 20 times more efficient, it doesn't matter because the hardware is 100 times more efficient for doing it kind of the dumb way, so to speak. So
Stephen, this leads to an interesting question, which is there any value in the question or any possibility of ever answering the question, quote, but does it actually understand, unquote? Turing, the Chinese room paradox of Searle, the question of at what point do you say it doesn't matter? The behavior is what it needs to be. I don't care if it, quote, really understands, unquote.
I think, you can ask about a human mind. Does it really understand? And
Yeah.
what you see from the outside is, well, yes, it came back with, it said the right thing. It said something which indicates to me that my model of it is it understood. So I think it's one of these things that is ultimately kind of that doesn't. Let me say one thing about quotes understanding. Okay, so when people tried to do natural language understanding for a long time, and they said in the 1980s, 1990s, people were like saying, well, we've got the system, it does natural language understanding. It was never clear what that meant. What does it mean to understand natural language? So when we built our Wolfram Alpha system in 2009, for the first time, we had a natural language understanding system where we had a very definite definition of what it meant to understand, which is we can take that English language input and we can translate it into computational language. And from that computational language, we can then, do this whole tower of computation. So for us, understanding was a very precise thing. It was take the English natural language, turn it into the precise computational language, and then we're off to the races doing all the kinds of computational things we can do. Now, it's interesting that that to me, that's a hard definition of understanding. It's different from the kind of definition you get with a large language model, which doesn't, actually, what's really interesting, all right, so, one of the things we released, 2 weeks ago now, a thing we've been doing with OpenAI, which is a Wolfram language and Wolfram Alpha plugin for ChatGPT. And so what happens is ChatGPT goes and does what it does, and we've trained it to basically know how to how to access Wolfram Alpha, how to write Wolfram language code.
Yeah.
And it goes off, and it's fascinating to see what it does, because it goes off, and for example, with Wolfram language, it'll try and write a little piece of code.
Yeah.
It'll discover that code did the wrong thing. It'll go back and it's very polite. It says, I apologize, something went wrong. And it'll rewrite the code and try again. And
Wow.
so for example, a very common thing in writing code, and this is something we're doing quite a lot with right now, is you have it right. Okay, one trick if you're using large language models. Okay, one bizarre trick is you have it generate something, and then you ask it, is what you just said correct? And sometimes it'll say no. You say, what on earth is going on here? Well, the way these things work is they're generating forwards one word at a time. So they never plan what they're doing.
Yeah.
So when you ask them afterwards, well, look at what you did before, then they have a chance of seeing what's going on. But it's this iterative process of you have it write a piece of code, you say write tests for that code, run the tests. Did the tests work? No, they didn't. Okay, go back and rewrite the code.
Okay, but you have to guide it. Stephen, I'm going to seize upon your phrase off to the races and observe that we are 53 minutes into our 45, and I have to give people a break. But Stephen, this has been a blessing, a boon, a wonderful opportunity to catch up with you personally, and also to have you to share these, I think, very actionable pieces of advice with people about how to recognize when the situation calls for this approach, and how to recognize when this is not the right kind of problem, and maybe how to rethink the problem. And all of those things were so much what we hoped would happen today. Thank you for your time.
My pleasure. Nice to see you.